Yeah, I accidentally had stopped the recording in the beginning, so, well, it doesn't matter. We'll get to this. So you see here we get if we put this 2 pi here, we get minus 1 over 4 pi. If we get 0 here, we get again minus 1 over 4 pi. Their difference is 0. So you see that the expected value of the product of x and y is 0, as is the expected value of x and the expected value of y. All of them are 0, but obviously they're not independent. I mean, once you know the value of y, you know the value of x. Well, not completely, you know. If you know that y is 0, then you know that x is either 1 or minus 1. There are no other possibilities there. So the probability that, for instance, if y is in some certain range, you get a probability that of x being in some other range, and you can make both of these separately as different from different from 0, and but they neither can happen together. I'll give an example here. So if I have here, I'll draw you an example. So I have the unit circle, and I have here so let me just give here example. So you see here I've marked these regions. The probability that x is between here, well then in these cases y is going to be either very close to 1 or minus 1. But x is between here. I mean, this could be like roughly 1/8 of the circle. And then here we could have 1/8 of the circle. So we have a certain probability of x being here, certain probability of y being here. But the probability that x is here and y is here is absolutely, it's 0, because those cannot happen together. All right. So it's not the case that they are independent. They're not independent. Because they're not independent, then this is an example of a case where they are they're not independent, but the product has the expected value of the the products. To understand that, this means that if the expected value of the product is not the product of the expected values, it's not independent. But if it is, it may be independent, maybe not. All right, moving on. Here, number 3, we said that x be a random vector. Here was a little bit of a, and let's say that it has this kind of a sample space where x ranges between 0 and 1, and then y ranges between x and x plus a for some a greater than 0. Now, I omitted accidentally that this was supposed to be a uniform distribution. So it's a uniform distribution in this region, continuous uniform distribution. So we first have to determine the sample space area. We know the sample space is what is the area. Well, it actually turns out that if we do the integration to find the area, it's just, integrate over 1. We get that the integral is 1a. So that this surface area is a, well, it's not that hard to understand. It's y is between x and a. So the height, if you will, at all points is a, and the width is 1. So the area is a. Hang on, there are a couple of typos still lurking there. Some equality signs were apparently missing. That should be better. All right, so expected value of x, well, we can integrate over x in this region, and it amounts to 1/2 x over a. Why is this so? Well, if we do the dy, we get x squared. You can calculate this. So if you calculate the inner integral, you get from x to x plus a x over a dy. So that comes down to xy over a and upper limit x plus a, lower limit x. So it comes down to x times x plus a minus x times x over a, which is equal to x times a over a, which is equal to x. So here, if you take the integral of this, then that's what you get at the upper limit x plus a, lower limit x, and then you do this x times x plus a minus x times x over a, and if you notice that this x times x cancel out, so the only thing that is left is x times a over a, which is equal to x. And then we take the outer integral, integrate x from 0 to 1. Well, that's x squared over 2. At the upper limit, that's 1 over 2, and lower limit, that's 0, so that amounts to 1/2. By similar manner, oh, there's accidentally a capital Y here, so let me just very quickly fix that for you. It should be the lowercase y, because that's the value of the integral, not the... All right, so if you do the same for y, you can verify it comes down to a plus 1 over 2. Now to calculate the covariance of x and y, we need to calculate the variances, not variance. We have to calculate the expected value of x minus the expected value of x times y minus the expected value of y. So we get this. I just wrote the answer here, but you can verify it fairly easily. Multiply that open, you get four terms there, and you can verify the integral fairly easily. Not going to write all the parts here, but if you want, I can write the inner part. So integrate from x to x plus a over x minus 1/2 sorry, dy. So I can show you how to do this integral here. This is the inner part, the inner integral, and I will calculate that for you. So it should come down to the integral from x to x plus a. I'm going to leave this 1 over a outside and get xy minus 1/2 y plus a plus 1 over 4 minus x. And then it comes down to x y squared over 2 minus y squared over 4 plus a plus 1 y minus So you get something that looks a bit like this. Too far away. Okay, so it comes down, it boils down to quite a bit of tweaking and turning there, but in the end, the dust settles down, and in fact, you get the covariance at 1/12. You can double check this with software if you don't like to do it by hand, but it does actually pan out pretty well.
Can I have?
Yeah.
Can you explain again why the area is integral from 0 to 1 x plus a x and 1? So what is
you mean this a, this one?
Yeah.
Okay, so look here. This is my sample space, and in my sample space, I gather all the values where x is between 0 and 1.
Yeah.
And then all the values of y, where y is between x and x plus a. So what happens is that I get something that looks like, I'll draw you a picture. So the area is something that looks like this, right?
Yeah.
So I need to calculate the area of this. One way to do that is just to simply calculate the surface integral over 1. The other possibility, of course, is you can verify this by many other means. You can verify that this is the height of this at each point is a, and the length of, or the width of this area is 1, so that's a times 1, so the area is a. It doesn't matter how you calculate this, but the surface area is the small a when you define it like this.
Yeah, yeah, I understand the small a, but I don't understand the number 1. Number 1, so what's the number 1 means?
This number 1 here.
No, number 1 in the middle.
Here.
Yeah.
Oh, it's just number 1. I mean that's the. I could just omit it. I can omit it. I can do it like this. There's nothing there. I'm just integrating over. The number 1 means just that, because I don't like to keep it empty. This this integral is over the surface. And what are we integrating over? We are integrating over 1, meaning that we're calculating each unit of area as 1, right?
That's
the interpretation there. And you can omit the 1 if you want. I mean, there's nothing there. It's just this integral.
And one more thing about the expected value of x and expected value of y.
Yep.
Since this is uniform distributed, I'm thinking that using the formula in the assignment 1, where the expected value of x is equal to b.
Good question. The thing about the thing about this is that that you are correct. You can use here the fact that it is true. It is perfect. It is true that you could use the first one, because if it's uniformly distributed, then the value of x, you can think of it as uniformly distributed. It's 1/2, because it's between 0 and 1, and this is between x and x plus a, so it's a plus 1/2. Yes, you could have it like this, but it's a little bit this is a little bit different, because you know this is not exactly the expected value of y does not actually conform to this, because the a is between x and x plus y, a, but it's not uniform distribution between just any x and x plus a, because it depends on x. So you have to calculate it via using the vector distribution here. Yeah, so you can calculate the density function of, there was a question What if I just calculate density function for random variable x as f of x as well to 1/1? The marginal density function of x is probably, it is probably just 1. That is true. But if I do the integral of integrate over this, but I'd have to, yes, that's a little bit, yeah, that's true. But where do you get where do you get the fx, which is the density function of x? I mean, if I say that it's a continuous uniform distribution in this area, I mean, remember that continuous distribution in the circle, in the unit circle. Did you remember what the density functions of x and y were? They were really terrible. They were like 2 times the square root of 1 minus x squared over pi, if you calculate the density function of x and y alone. You see, the trick here is that it's uniformly distributed in this, how should I say, it's not a rectangle. What is, I forget what it's called in English, this shape. It's uniformly distributed. Yeah, parallelogram. It's terrible, and my tongue gets tight. Yeah, parallelogram. It's uniformly distributed in here. So while you can actually derive the result that x is uniformly distributed between 0 and 1. Y is not uniformly distributed because where y is distributed depends on x. And that's what we are doing here. So we notice that the expected value of x is 1/2, as you would expect, because it's between 0 and 1, it's uniform. But because y is between x and x plus a, then the expected value of y is a plus 1/2. And now this covariance integral, when we calculate this, it becomes a bit heavy, but it comes down to 1/12. You can toss it into software if you want to. I'm not interested in going through all the algebra. We don't have time to go through all the algebra here. But you can get 1/12. Yeah, exactly. That's true. You're asking question if I cannot calculate x and y alone, I have to calculate the density function f of, yes, that's how it should be done. Yeah, that's how it should be done. Because if you think of it, that it's uniformly distributed in some area, the shape of the area, I mean, if it's a perfect rectangle and it's uniformly distributed, then that's a special case where you can get x and y just separately, because then they will be independent. But if it's uniform distributed in any other shape, then it's usually not, they're not usually independent. And in this case, they're not independent, as you can verify from the covariance being non-zero. Covariance is 1/12. The thing is, we can then calculate the correlation. I mean, in order to calculate the correlation, we have to calculate the variances. And what happens is that if we calculate the expected value of x squared, we can toss it in here. It's really easy because this just becomes x squared here. So the outer one doesn't have a big effect on it. So it all comes down to 1/3. The expected value of y squared becomes a little bit more tricky, but not by much. And you can see here, this is from the same uniform distribution. This actually conforms to pretty much the same as in the uniform distributions situation. We get the variance of y and we get the variance of x. And if we divide the correlation, the correlation is, remember that the correlation is the covariance of x and y divided by the square root of the product of the variances, right? The correlation, remember that this is the correlation. So you normalize the covariance dividing by the product of the square root of the product of the of the variances, and that's gonna amount to divide by the square root of 12. There's a square root of 12 in the divisor, so they cancel this 12 here because 1 over 12 these are in the divisor, and the only part is left is a squared plus 1. So we get the correlation is 1 over the square root of a squared plus 1. Looks pretty weird, but let's think about this. Let's look at this. Let's look at this picture to get an intuition. What does this mean? If A is very small, then this region is very narrow, right? If A is very small, this region is very narrow. At the extreme, if A is almost 0, then all the values of X and Y fall on this line. But if A is all but 0, this correlation is going to be pretty much equal to 1. I don't know if you remember this or if you read this in the lecture slides, but the correlation is equal to 1 if and only if the probability that X and Y always fall on the same line is 1. So if correlation is very close to 1, then X and Y will fall on roughly a straight line. And this is what you will get. If A is very close to 0, this is very close to 1. Again, if A is very big, then this correlation tends to be rather small. And that, as it would be, I mean, think about it. If you take Y, it's randomly distributed like this. If you put A to be very, very big, so this is a very, very wide. So yes, the values of values of Y tend to be somewhat larger in this edge where X is large, but it's not a big difference if this is a very wide region, right? So the correlation will be small. The purpose of this question, or this task, was to give you an idea of how correlation behaves when there's a sort of like a linear, there's clearly a linear dependency here, but it becomes weaker. There's more and more randomness inherent inside Y that doesn't depend on X, purely based on this A. I mean, the smaller the A is, the more closely Y is simply determined by X. And the larger the A is, the more random Y is with respect to X. I hope you understand what I'm meaning here. I'm hoping that this picture here will give you this idea. So if this region becomes narrow, then the dependency is very strong. And if this region is very, very, I mean, if it's huge, if it's this big, right? And then there is only a minor effect of X on the value of Y. And this can be seen from the fact that this correlation will be diminishing, smaller. And if A is small, you know, the variance is small, the correlation goes towards 1. All right. The idea here is to give you an idea that you get this intuition about what correlation might mean. So the thing is, the dependency may be actually completely linear, like in this case, but there is inherent other randomness at Y. And then the correlation will be small. Number 4, we have this so-called Cauchy distribution. This was fairly simple. We just have to show that if X is Cauchy distributed, then it doesn't have an expected value. You might think that this is completely ridiculous, the Cauchy distribution. A variant of the Cauchy distribution emerges if you take, let me think. I think it emerges if you take a random, uniformly distributed random point on the unit circle. It may be with somewhat different values here, but let's take a unit circle, one that is not exactly unit circle, but it's been lifted here like So you have a circle. This is a unit circle, but it's not on the origin. It's touching the origin over there, right? And then we take a uniform random point on the uniformly distributed random point on the edge there. It can be anywhere else except not at the top of the circle. That's taken out. That value is not included. So a uniformly distributed otherwise here on the edge of the circle, but not here on the top of the circle. Uniform distribution. And then we take that point and we draw this line here. And that is our random variable x. It turns out that this results in Cauchy distribution. Not that we need to figure that out, but I maybe if we have time, or maybe in the examples, I put one example where we derive this. So you transform that. You need some trigonometrical functions and so forth, but then you can come up with that. So it leads into this this function f of x as the density function. It doesn't have an expected value. I mean, this is completely symmetric around the origin, and you would expect that that the expected value might be 0, but in fact it's not. The thing is, if you calculate this integral, if you calculate the expected value of x, so it's f of x times x, and you put here x times this density function, so it's x over this. If I take the 1 over pi out of here as a multiplier, then the integral of this x over 1 plus x squared, it comes out at 1/2 times the logarithm of x squared plus 1. Oh, there's again a typo there, slash missing somewhere. Just a second. Over there. Yeah. All right, that's better. So so the function x over 1 plus x squared, I mean, if you take the integral of that, it becomes 1 over 2 times log x squared plus 1. If you let x approach infinity or minus infinity, this goes towards infinity. So this doesn't exist. Yes, infinity and beyond. That is true. This doesn't converge. So you see, we have a problem here. Then we need to show that, in fact, the expected value of the square root of x is, take the absolute value of x and take the square root of that, then that does have an expected value. This is the weirdest thing. We can have this is just a curiosity, but we can have a perfectly legitimate random distribution, one that doesn't have an expected value, but for which we can define then other functions of that, which will have expected values. For example, the square root of the absolute value. So it's not an easy integral to calculate, but remember that we have to only establish the fact that this converges. So if you took the maths 3 before these are the sort of things that you would have calculated and figured out, does this converge? But if you look at this, there's an absolute value here. This is always positive, right? So this is, in fact, you can put this as 2. We take this into 2 parts, from 0 to infinity and from minus infinity to 0. They're symmetric, so that's just 2 times from 0 to infinity. And then we can just take the pi here in front. And we can just look at this integral function here, this square root of x over 1 plus x squared. This is, again, not an easy integral to calculate, and we don't actually even need to calculate it. We can only need to find the upper limit. Again, we chop it into pieces. So we chop this into 2 pieces, from 0 to 1, and then from 1 to infinity. So you see here we do it from 0 to 1, and here we do it from 1 to infinity. And this one, because 1 plus x squared that's a divisor, so we're dividing it by something greater than 1. So we can make this, between 0 and 1, we can make this bigger by omitting this x squared, because we're just dividing by a number that is slightly smaller than we were dividing before. So we have this square root of x then. And then for the values from 1 to infinity, we can take this x squared, we can divide it by something smaller than x squared plus 1, namely just x squared. So this comes down to x to the 3 over 2, which at 0 to infinity, that's fine. This, on the other hand, comes out at that's 1/2, that's x to the minus 1.5. And the integral of that is roughly equal to the 1 over the square root of x. And then that converges. Both of these converge, clearly. So we get that whatever this is, it's smaller than that, and that's a finite number. So that's good enough for us. To establish that it exists, we just show that there is some number which is an upper limit for this. Shouldn't be too hard. Why I wanted this example here? No, expected value of x cannot be 0. That is the weirdest thing. It's clearly a symmetric distribution. It clearly has a middle point at 0. You would expect it to be the expected value at 0, but it's not.
Can I have a question?
Yep.
What if I have a set of number, for example, -2, -1, 0, 1, and 2, and then is it uniform distributed? So the expected value of that set would be 0, I guess.
So can you, so you have a uniformly distributed, can you type the range? So I couldn't finally understand what you meant. If you can type.
Yeah.
Okay, yeah. This is your range, and this is a discrete variable.
Yeah.
Uniform distributed, yeah?
Yeah.
So it has obviously it has a expected value 0, yes?
Yeah. So when you say that it's not possible to have the expected value equal to 0?
Oh, this one, definitely. I'm talking about this example, this Cauchy distribution.
I mean,
I'm talking about this question number 4. I'm not sure if you were talking about something else, but I mean, I was talking about this Cauchy distribution here. In here, the expected value is not exist.
I mean, yes, I understand what you mean. So, in some case, the expected value is equal to 0, but in some case, like in this example, the expected value is equal to 0, but it doesn't have any meaning, right?
Well, no. In this Cauchy distribution situation, you have a distribution which does not have an expected value at all. I mean, you have to understand the expected value is defined as basically the result of this integral. And if this integral here doesn't exist, if it doesn't have a limit, if it doesn't have a sensible value, then it doesn't have a expected value. That's
Yeah.
just that it. The thing is, this doesn't converge. This doesn't converge. It goes, I mean, if you go from 0 to infinity, it has an infinite area. And then if you go from 0 to minus infinity, it has an infinite minus infinity. So this is not a well-defined situation. If you make this integral, look at this integral. If you make this from minus a to a, any fixed a,
Yes.
minus a to a, then this integral here, this expected value of it, this will result in 0.
Yes.
But it doesn't converge up to infinity. And the thing about it is that it has to be, the integral has to be defined separately at infinity and minus infinity.
So it's still, first of all, if we don't using the infinity, but if we using the some specific number a, so the expected value can be.
Yeah, I mean, you have to understand that these kind of pathological situations can only appear when we have an infinite range for the variable. They won't happen if we have if the sample space is limited, then this cannot happen.
Yeah. Okay, I understand.
Yeah. It shouldn't. Well, I mean, not in any of our examples. If it can happen, then not in any of. I'm not going to promise that I started thinking that maybe I can come up with a really pathological distribution. Yeah, exactly. Infinity is not a number. No, it's not a number. You cannot, I mean, yes, if you think of this as a number and this is a number, then subtract that at that number and that number, then it looks like you get a 0, but it won't. Because you cannot calculate it at infinity. It's not a number. That's a good point. Don't be too alarmed. If you don't understand this, why this is so, or this, then don't worry about it too much. We're not going to be talking about these kind of distributions. I just wanted those of you who are wondering, I mean, you can do all kinds of weird things with integrals, and even the formulas I mentioned, that sometimes these integrals don't exist. Sometimes the variance, I mean, it can be, you can define a distribution which has an expected value but no variance, for instance. That's possible. I'm not going to go any deeper into this, I mean, because it's not required material. I just wanted to give this an example. Okay, let's go to the next one. We have a uniform continuous distribution between 0 and 1 and n. We know the variance already and the expected value. We calculated them. Now calculate the standard deviation and calculate the probability that x minus mu is greater than 2 times the standard deviation, knowing that x is uniformly distributed. This is a trick question. If we calculate the variance based on what we did before, it's in the variance is n squared over 12, so that the standard deviation is n over 2 times 2 times the square root of 3. So, and we know that the expected value is n over 2 in this case. Let's assume now that x minus mu is greater than 2 times sigma. And then if we rearranged it, we get that x is greater than n over the square root of 3 plus n over 2. N over square root of 3 is less than 2. So this sum is greater than n. Well, obviously this is impossible because we assume that this, so the probability of this happening is 0 because it's uniformly distributed between 0 and n. And for it to be greater than 2 times sigma means that it would be greater than n, which is impossible. Then we assume that x minus mu is smaller than minus 2 sigma. Here, I mean, this x minus mu greater than absolute value greater than 2 sigma, then there are 2 possibilities. This is greater than sigma, or this is smaller than minus 2 sigma. If it's smaller than minus 2 sigma, we can rewrite this again that x minus n over 2 is smaller than or equal to minus 2 times sigma, and then we can rearrange this by adding, by moving the n over 2 on the other hand side. And we notice that n over 2 is in fact smaller than n over the square root of 3. So this becomes that x is smaller than or equal to something that is smaller than 0. Again, impossible. So the probability that x is greater than x minus mu is greater than 2 times sigma is in fact 0. So there you have it. The probability is 0. But if you use the Chebyshev inequality to compare these results, well, if you look at that inequality, it says directly that the probability that x minus mu is greater than or equal to, and then you have k times sigma, it's smaller than or equal to 1 over k squared. In this case, k is 2, so that's 1 over 4. Here is admissible. If you find this hard to calculate, you can try it for some particular values and notice that the values you get are larger than the limits of the distribution in A. So you see that the Chebyshev inequality is not, it gives you 25% upper limit for something happening when in fact, if you have a uniform distribution, that kind of thing can never happen. So it's not a very good limit. But sometimes if the only thing you know is the expected value and the variance, then sometimes it's the best you can do. We can come up with really pathological situations like a distribution where the expected value is 0, and then there are two different values, -1 and 1, let's say, and these occur with certain probability, like 1 over k to the n, where k is some large number. What you get is you can come up with a different situation where the variance goes smaller and smaller, but there are still possible outliers there on the edges. So you have this 0 case, which has a high probability, and then there's the limit cases at the edges with smaller and smaller probabilities. So the variance goes down and the standard deviation goes down as these becomes smaller and smaller. They are still possible, and then the Chebyshev inequality gives the actual probability of getting those values. But that's the limit. That's the worst case scenario. All right, moving on. Number 6, prove theorem 3.31. Well, this was again just, it's not that. Just throw it into the formula. What is the moment generating function of y? Well, let's calculate it. It's the expected value of e to the ty, which is the expected value of e to the t times a x plus t times b, multiplying a x plus b by t. And we get this product expected value of this. And so we take this out because this is a constant. So we can take it here times the expected value of this. We use at as u. So we get here that this is some e to the ux, which means that it's mu. So it's e to the bt at. M at at. Actually, yeah, there was a question here. When does equal happen in the case of t inequality? So the case of equal happens when you have a situation where you have this distribution where there's a -1, 0, 1. This is your sample space, and the probability of -1 is 1 over k. 1 over, let's say, n, which is also the probability of 1, and probability of 0 is 1 minus 1, 2 over n. And now when you do this by letting the n grow, you can calculate, and there's you can find it. I think you can find it in the Wikipedia page. Actually, I don't have this. This has been a little while. Let me just check. Oh, it's a little bit different. Let me just share that with you. Okay, you can see this pane. Here's an example. You can find the sharpness of the bond. Let's define x in this case, in this way. So there's -1 with probability 1 over 2 times k squared, and 0 with probability 1 minus 1 over k squared, and 1 with probability 1 over 2 times k squared. You can calculate here easily because it's symmetric and limited, bounded. Then its expected value is 0. You can also calculate the standard deviation at 1 over k, and you can find that the probability that you get one of these extremal values is 1 over k squared. So this is the only distribution where this limit case happens. If there's any other kind of distribution, then the T inequality gives an inaccurate result. Does this answer your question? Oh, okay. All right. So this one was this week's things. I'll post a fixed. Well, you said it's hard to imagine why there's. Well, yeah. All right. You have 2 questions. Please give me these questions that are relevant for everyone, if you want.
All right. The first one is that for me, at least, it's not possible to see my own papers that were assessed. So the feedback from other people on my weekly exercises are not visible to me.
I'll make sure that you get that visible. That's I need to. Okay, I need to okay the reviews before that happens, and I'll do that. I mean, I had forgotten to do that. It's good that you mentioned that. I will do it right after we finish this session to make sure that the first and the second one will be visible to you. Okay, that's good. Good.
All right. Furthermore, sometimes you update the PRC slides document with new additions or corrections or otherwise changes.
Yeah.
It would be kind of nice if on the Moodle page it would say when was the last update, because I think I and at least some other people, we localize these, and I'm never sure if I have the most recent version.
Okay, that's good. Good. Then what I will do is the next time I update it, I will mention that now it contains this material and then the date when it was updated. I'll do that.
All right, perfect. And my last question is not really relevant for anyone else. So.
All right, yeah, you can ask it. Send me a personal message or something like this. I can answer it if you want.
It can also be here. It's not private, but.
Okay. Yeah. Anyone else have any questions? 4. So okay, here's a question. Discrete and continuous case and integral from a -a to a, it has expected value 0 from. So someone asked me this: if we have a discrete and continuous, so if we have a continuous case which is symmetric, and symmetric meaning that the function is density function is symmetric around 0, meaning that it's what we call a even function. Even function meaning that f at -x equals f at x. If that's the density function and it's bounded, discrete or continuous, doesn't matter, and it's completely symmetric, then it's going the expected value is going to be the centermost value, in this case 0. Okay, you asked the question, what happens if I find density function for x and y separately and integrate x? Let's look at that question. Let's look at that question now. 3a. Now, I'm not sure what you mean if you say what happens if you find the density function for x and y separately. You can find them separately, but do you mean you calculate the separate density functions by using the marginal density function so that you integrate over, let's say, the integral, so that you have this fxy, and then you integrate this so that you get rid of the y and you get, so yeah. All right, if this is what you mean, then that it should have, the same thing should happen. The same thing should happen. That's pretty much what should happen. The same thing should happen. I mean, the marginal density function should give you the distribution of x. The marginal density function should give you the distribution of y separately.
Can you explain for me further about the expected value of y? I mean, that two layers integrals. I mean, the meaning of that integral for y.
So let me just, I'll draw this. So I'll draw this for y. So in order to get that for y, we have to take the f of xy, which is equal to 1a, 1 over a. So we start with this. This is our density function for both x and y together. And now, in order to find the fy of y, then we have to integrate this fxy dx from 0 to 1. We have to just calculate the integral of this so that the x there goes away. So we get here x over a at 1 and 0. And that comes down at 1 over. That comes down at 1 over a. Let me think. Yes. No, it shouldn't be this. Because I have to figure out this. I can do this for x, but I can't do this for. Hey, that's a very good question. I'll have to double check that. I'll get back to you on that.
Because I noticed one thing, that when y is less than a, so I mean I found a different function.
It should be. Yeah.
Yeah. I mean,
yeah, it should be different.
You're
correct. Because if I look at just this picture, then you will notice that so if you look at this picture, and I'm going to put it on the side here to indicate that this is now, we're now looking at this, how this y works. So we have less probability here and more probability here. So it should depend on the y, so that it increases here, 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 here. It should, depending on what that a is, if it's larger than 1 or smaller than 1, you get a different result. I'll have to yeah, you can't integrate it from 0 to 1 directly, because then you have to flip this picture. So if you have that x is y is between x and x plus a, then you have to figure out what the value of x is. So you have it differently between 0, 1, and yeah. It works so far as to calculate the marginal distribution function, but when you plug the formula the function for use in the expected value formula. It's hard to determine the, yes, that's true. Yeah, that's true. The integral bounds here, if you do it differently from this, the integral bounds for the marginal density functions are very hard to come up with, because you have to factor in the fact that, you know that x is, so y is between x and x plus a, right? But x is between 0 and 1. So to find out the values of x, you have to, it depends on the a in such a way that if a is very big, for instance, or if a is very small, then, well, basically what you should be able to do is find this function, which is the height of this area, but then it should stop at a place where x equal 1. So it's going to be hard to determine the integral bound. I wasn't actually thinking of that. I applaud you, and I'm really glad that many of you thought about this in terms of the marginal density functions, because those are harder. And in this case, any other questions, any questions regarding the marginal density functions, if anything that would have required you to calculate the marginal density function of y, it would have resulted in a much harder question. So if you went that way, you got into trouble. I guess many of you were able to do that. And if you did do that, then I'm more than glad that you did. It's hard work. Yeah. Any other questions here?
Hi, I'm thinking in the way. Sorry. Can you see the screen?
Yeah, I can see the screen. Just let me
Because,
bigger.
because I'm thinking that if the x go from this to this is y, but the value of y still, it still remain constant, because even when x is 0, y go from 0 to a.
Now I'm not seeing it very well. Can you raise it a little bit? I'm all right. Yeah.
Sorry. Yeah. So x is 0.
Yeah.
And y do take the value from 0 to a.
Yeah.
And x move a little bit further to here.
Yeah.
Y still take the value from here to here, and so on. So I think that the value of y still remain constant throughout the range of 0 to 1. Is that right?
Well, the range, the value of y ranges from x to x plus a. But
Yes.
if x moves, the lower limit goes a little bit up, so you get slightly different values of y depending on x, because the x is increasing. So first, the marginal density, the marginal distribution is perhaps easiest to, if you take that picture and we do it like this, then if we look at the marginal, if you look at this picture, which was shown, so everything is fine in terms of x here, because x is at all times, it's from 0 to 1. But the problem comes with y, because y is from x to x plus a. So if x is here, then the expected value of y is in fact x plus 1/2 a. So if x is here, the expected value of y would be 1/2 a. But if x is here, then it's 1/2 a plus 1.
Yeah, I understand.
Yeah. Yeah. That's why this actually comes from. If I share you're seeing still this. If you're seeing the shared thing, this a plus 1 over 2. So this is really the average of those two. This expected value at the edges. It's linear, so you would expect it to be this average. So a over 2 and 1 over 2. So a plus 1 over 2, and they're average there. Yeah, there was a, this is a good question. My current problem, the worst problem I have currently for this, to put the MATLAB questions into the exam, the worst hurdle I have for this is that my laptop doesn't, I only have the online MATLAB version, and it's really cumbersome to write M files here and then use that on those. I don't have access to my office in which I had these really nice MATLAB tasks, and I was thinking of doing the electronic exam this year. The others are doing an electronic exam, but I'm honestly, I'm not sure yet. I'm not sure about how the exam will go. I mean, the situation is very uncertain. I'm not sure if we can arrange for regular exams at all. They're trying to, but I'm not sure. If we are going to arrange for regular exams, then you have a choice between just regular pen and paper exam, in which case there is no MATLAB, and then possibly have access to the electronic exam, in which case you will be able to use MATLAB, but then they would have slightly different questions. That's all I can really, yeah. I'm not going to put complicated, I promise you, I'll do the questions in such a way that it won't require complicated calculus. That's the best I can promise. I'll do my best so that any problems you have with calculus is not going to have a huge effect on your grade. If you have problems with calculus, I'm trying to make it, this is not a calculus course, but it does require a little bit of calculus. So it's a relevant question. I wish I could say something more definite now, but I honestly don't know how the exam season is going to be this year. I have no idea how we're going to handle it. No idea at all. Sorry, I can't give a better answer here, but that's all I have. We don't know how long these quarantine measures are going to be taking. So how long the campus is going to be closed. If it's going to be closed on May, we're going to have hell to pay on exam week. I have no idea how we will handle that. None. It's up to the admins, they'll tell me, but then we'll be in a hurry, and yeah, terribly sorry. Yeah. Any other questions? All right.
Well, I could ask the personal question.
Well, if it's of the nature that you don't want anyone else to hear it.
Oh, sure, no worries. It's about the amount of people we're supposed to review, because last time I had 2 people, this time I had 3 people. Is there any sort of?
Yeah. The thing is, it assigns those randomly. It's supposed to assign 3 people to everyone. However, the random generator there doesn't work perfectly. Sometimes it just gives some people 2. I have no idea why this is so. It's not perfect. It's not even very good. So don't worry. Right. Do the assignments you've been given and don't worry about it. Yeah. Anything else? Okay. I think we are at the end of the timeline here. I think we'll have our lecture tomorrow at 10 as per the schedule. I'll post again a link, and I'll try and figure out tomorrow afternoon how to make those videos available. If nothing else works, if I don't get the OneDrive links working properly, then I'll revert to putting them on YouTube or something like this. You'll get them in the next few days. All right. I wish you all the best. I'll see you guys tomorrow, and stay safe.